Gibbs energy and equilibrium. You can calculate the standard Gibbs energy of a reaction, okay, from thermodynamic table. So you can look it up. All you have to do is figure out delta H. We've learned how to do this earlier, right? Delta H for a reaction. And delta S for a reaction, we just covered that, right? So delta H minus T delta S would give you delta G. Or you can just look up what the standard Gibbs energy of formation of your products and then subtract the standard Gibbs energy of formation of reactants. Delta G formation is defined in a manner similar to delta H formation. If you remember, we said delta H of a reaction is delta H formation of products minus delta H formation of reactants. Same definition for delta G of reactions. Okay? Now, why are we interested in delta G, the standard Gibbs energy of a reaction? Because that allows us to predict the equilibrium constant. So we can actually calculate KEQ for a reaction from the delta G for that reaction, standard Gibbs energy for the reaction. Now, the Gibbs energy for an actual reaction mixture depends on what your reaction quotient is. Okay, so the delta G would be equal to the standard delta G, okay, plus RT times the natural log of your reaction quotient. And so what happens is, if your reaction quotient equals to KQ, what happens? Then your delta G would approach zero. You'd reach equilibrium, okay? So delta G, the reaction Gibbs energy, is equal to zero at equilibrium. So that means, okay, you can say then that delta G, let me point that out here, is equal to delta G naught plus RTL and Q. So if this thing is zero, and then Q would be equal to KEQ. What do you get now? So you get 0 equals delta G naught for the reaction plus RT natural log of KEQ, which we can rearrange into this equation right here. So delta G naught for a reaction is just equal to negative RT natural log of KEQ, or you can use base 10 log for that. Okay? So if I know my KEQ, I can get delta G naught. What if I knew delta G naught? How do I solve for my KEQ? I divide both sides by negative RT. So delta G naught over RT, negative, equals ln of KEQ. And then I can just solve for KEQ. Okay? KEQ equals e to the negative delta G naught over RT. So where can you find delta G naught? You can look it up from the web book or at NIST, or you can look at the back of your book. So let's go back to that webbook.nist.gov. Let's say I wanted to do NH3, okay, gas phase. Do a search, ammonia. You'll see here, there's no delta G naught here. It doesn't have that. It has delta H and S. But if you can calculate delta H and delta S, that should allow you to calculate delta G. Okay? So let's apply that. Let's say you found your delta G naught, standard Gibbs energy of your reaction, to be 300 kilojoules. What would be your KEQ? What's our formula? KEQ equals e to the negative delta G naught over RT. That's going to be equal to what? E to the negative 300 times 10 to the third joules. Okay. Okay, that's per mole of reaction. Okay. It has to be in reference to a reaction, so let's call that per mole. R is 8.314 joules per Kelvin per mole. And our temperature is What's our temperature? Unless otherwise specified, we're going to assume 298 Kelvin. Right? So Kelvin cancels out, moles cancel out, joules cancel out. That's a unitless quantity. So what would that be? 300 times 1,000 divided by 8.314 divided by 298. That's e to the negative 121. Okay? And what is e to the negative 121? I make that negative. Inverse log. So inverse log, that's e to the x. That is 2.6 times 10 to the negative 2.6 times 10 to the negative 53. What does a very small KEQ value like this mean? At equilibrium, how far has the reaction gone? Hardly, right? It's hardly gone forward. Most of the reactants are still there. We have very, very, very small trace amounts of products formed. That's a very small KEQ. Is that consistent with our notion of delta G being non-spontaneous if it's positive? This is a very positive number, right? A very positive number means you're going to have a very small KEQ. Remember, you want exergonic reactions, and those are the spontaneous reactions. So this reaction is not going to go very far. What would it be if it's the other way around? If this was negative, if it was the other way around, if it was e to the positive 121, what would it be? 121 inverse e to the x would be 3.5 times 10 to the 52. Okay, so if delta G was negative, 300 kilojoules per mole, then you're going to get a KEQ, which is very large. It's going to go all the way to the product side. Okay, so a negative delta G means reaction KEQ is going to be large. You're favoring the product. A positive delta G means you're favoring the reactants at equilibrium. So, quick check. Which reaction has a larger KEQ? Reaction with delta G naught of plus 30 kilojoules, one with the negative 30 kilojoules. Is it A or B? More negative delta G, farther the reaction goes, the larger the KEQ. And let's calculate delta G and Kp for this reaction. Well, we calculated delta S for this earlier. What was it? Let's calculate delta H and delta G since I don't have access to Gibbs and delta G of formation. Let's look at delta H and delta S for this. Okay, delta H for this reaction would be 1. Delta H formation of NH3 minus, oops, this should be a 2 right there, okay? So 2 times minus delta H formation of N2 plus delta H formation of H2. What are these numbers? Let's look it up. NH3 delta H formation of NH3 gas is negative 45.9 kilojoules per mole. This was NH3, huh? Yeah. So negative 45.9 kilojoules per mole. How many moles of ammonia do I have here? 2. Okay. Times 2 moles. Okay. 2 moles ammonia per mole of reaction. Okay. Minus, what's the delta H formation of N2? It's going to be 1 mole N2 times Do I even need to look up delta H formation of N2? Element in its standard state, so that's going to be 0, right? Plus 3 moles of O2. What's the delta H formation of O2? I mean H2. Again, H2, you don't need to look it up. It's going to be 0. So what is this number? 2 times negative 45.9. Negative 91.8. kilojoules. Okay? What's our delta S? We did this earlier. Well, you remember what our delta S was? Let's go back. Here. We calculated delta S to be negative 198.11 joules per Kelvin. Negative 198.11 joules per Kelvin. Be very careful when you're combining your delta H and delta S. Delta H values are generally tabulated in kilojoules per mole, whereas delta S values are tabulated in joules per Kelvin per mole. So what's our delta G of our reaction? It's going to be delta H minus T delta S. What's our delta H? H is negative 91.8 kilojoules. So I'm going to change that to joules. Okay. I'm just going to keep it kilojoules. Okay, minus, what's our temperature? Unless otherwise specified, we're dealing with 298 Kelvin times negative 198.11 joules per Kelvin. Okay. And one of these I have to convert to the other unit. What unit should I be converting? I want to make this kilojoules, so that is 298 times 198. That's 59,000 joules, so that's 59 kilojoules. Okay, negative, negative, so that's positive. 59 kilojoules. 59.0. And this is negative 91.8 kilojoules. Okay. So our standard Gibbs energy is, so that's divided by 1,000. That gives it in kilojoules. We add that to negative 91.8. That gives you negative 32.8 kilojoules. Right? How do I calculate Kp from that one? Kp is equal to e to the negative delta G naught over RT. Same type of calculation we did earlier. Okay? And that should be it.